Hamilton-Jacobi Hartree-Fock equation with results concerning viscosity solutions, concentration compactness, mean field games, etc. And among other awards, he is Commandeur in the National Order of the Légion d'honneur in France, and member of the Academies of Science of several countries. Let me say also that he has received numerous awards, including the Fields Medal in 1994. And today he's going to give a talk on mean field games, well-posedness, singularities, and beyond. So thank you very much for having accepted the invitation to this conference, and you can start as well.
Okay, so thank you very much for the introduction, Enrique. I seem to have a problem with sharing my screen. First of all, do you solutions thanks to? Okay, I was careful, and let's begin. Well, good morning to everybody. I'm not sure it's morning for all of the participants. It's certainly morning where I stand. It's in fact a little bit early for my taste, but that's life with time changes. Thank you very much for the organization of this meeting, for inviting me, and thank you again, Enrique, for your nice words. Okay, so you must see now the title appearing, which is about mean field games, and more precisely about the issues concerning well-posedness, singularities, and beyond, with a question mark.
So sorry, can you see yes, the slides?
For me, it's okay. What about the others? Enrique, do you see the slides?
Yeah, it's okay. It's
okay. Okay, thanks. Thanks a lot. So sorry for this mess up, and thank you, Anna, for your help. So let's move to the summary briefly. So next slide, please. Okay, so introduction, which is going to be short. I will explain a little bit the main results, and then explain a little bit more about the proof in the so-called final states case, and in fact, we'll mention that all this is can be viewed as an observation on Cauchy-Lipschitz theorem, where typically you're in PDE or ODEs involving several spaces. Some proof, some singularities, and beyond. I might also mention, hearing Enrique, the other Enrique Zozois lecture, I might mention connections with his lectures about the possibility of making numerical computations using neural nets in infinite dimensions. Okay, so introduction. Mean field games. Several of you sitting in the audience or listening to the meeting have heard me talking about mean field games. I still have to recall what they are. So basically, if we want to summarize everything in one sentence, it's about so-called self-consistent models for large populations of agents, of players, whatever you want to call them. Okay, and all this is being done in a mean field sense, which is a classical word in statistical mechanics and statistical physics. So just to give an example of the type of equations that we are interested in, let me look at the situation where time is continuous, space is continuous. Then the object of interest, the variable, okay, the object of interest is going to be one, for instance, if you have only one population, function, scalar function, taking values in R, a function which is defined on a space which is an infinite dimensional space, since it depends, okay, on T, that's finite dimensional, one dimensional, that's time, X, which is in general finite dimensional, although it could be large dimensionality, it could have a large dimensionality, so that's X, and X stands for the state variable of a generic member of the population, a generic agent, okay? So this is typically X could be for the agent, its wealth, its age, its size, its weight, whatever, okay? So that's part of the modeling. That's how you described an element of the population. But then the main or the most important variable is a state not of an individual agent, but of the whole population. So the state of the whole population is a measure. In general, non-negative measures. So basically, you count how many people there are which are of age, let's say 68. That's my age, not random, or which weigh more than X kilos, whatever. Okay, so you count, and that's your counting measure. And in general, it's a non-negative measure. So if you have a fixed number of agents, it's a probability measure. In general, it's just a non-negative measures because people can enter the game or leave the game, can have an activity or have no activity whatsoever. So it may really, one should keep in mind that probability measure is a very strong assumption. It means that something is fixed. Okay. So in general, mean field games are going to be equations involving this scalar function u on this infinite dimensional space, which is basically a space of measures, and possibly also, and in general, you also have a few finite dimensional variables. Then the equations can be written in a somewhat concise or abstract way by du over dt plus d plus t plus n equals 0. So D stands for decision, that's so-called decision block. You can think it's an optimal control block, that the decision is done individually by each individual agent as an optimal control decision, or it can be a much simpler type of decision process. T is transport. So what does that mean? This means that whenever an agent chooses an action, and when they choose an action, of course, the state of the population will change. And so all the individual decisions will transport the state of the population. So it's a transporter. And on top of that, you have in general all kinds of noises, random effects, and so on that I summarize by this term N. Of course, the fact that writing those blocks as separate blocks is already a simplifying assumption, but I don't want to get into too much technicalities or too much generalities. Okay, so what was introduced already some time ago for mean field games is that instead of having equations on the space of measures or on the space of probability measures, you can replace, you can try to write down, equations which are set in a Banner or an Hilbert space, or typically Hilbert space, if we are thinking of the probability space equipped with the 2 Wasserstein distance. Okay, so like a space of L2 random variables, square integrable random variables. And indeed, the way to think about the connections between an equation set in the space of random variable and an equation set in the space of measure is to say, well, I can always define, if I have a measure that depends on probability measures, I can always define a function on the space of random variable by saying that the effects of the action on the random variable is really the action on the low of the random variable. So in other words, we are looking at functions on the space of random variable that depend only on the low, some kind of symmetry condition. Next slide, please. So I passed very briefly on the equation in Hilbert space, and in fact, it's exactly the same as the one in the finite state space. So let me comment a little bit. So typically, if you leave aside the noise, which are certainly not in general a full Laplacian, it might be a bunch of second-order terms, non-local terms, and so on, but I don't want to get there. So in a finite state space, which means that each agent has only, I mean, the state of an agent is described only with a finite set of variables, right? So you can be in position 1, 2, 3, up to k. Then what you are dealing with is, of course, replacing the dependence with respect to that finite state, finite number of states. What you're left with is now a system of equations of, let's say the unknown is capital U from Rk into Rk, also depending on time. And what you can see on this equation is that this is like a non-conservative first-order system, non-linear first-order system of equations. And the main characteristic is that the transport term, namely the term A, B is like a nonlinear source term. A is the same vector field for all the components of U. That's the only modeling restriction you have for such systems. On the other hand, that's just an example, okay? On the other hand, if you are looking at the equations in the space of measures, this is the horrible-looking equations where you will recognize, okay, du over dt, everybody can see that one. The second one, A naught, is really, you can think that if it's optimal control decision-making, then this is like a Hamilton-Jacobi term. Then the third term, which is like this directional derivative with respect to the measure. So it's differentiating U of the unknown function that you may call the value function with respect to M, and in a direction which is a transport operator that on top of everything depends on M, depends on dxu. So all those derivatives are quite strongly coupled. And then you may have noise terms, and so typically nu stands for the situation where all the players have their own little noise, and alpha stands for the amount of common noise. Here, those are bounding noise. And so it leads to Laplace-like operator. So several terms, I'm not going to comment all of them. Typically, you have this Laplacian with respect to the x variable in U. That's usual diffusion associated to Brownian motion in finite D. But it has also an effect on the transport of the measure. So you're now transporting the measure by the heat operator, I mean by the Laplace term. And you have more complicated terms, which when you have common noise, which are second derivatives with respect to M. So we are dealing with an infinite dimensional equations and with second order operators. And then there is the fact that you may have a Brownian motions acting in the x and acting on M creates such coupling terms between derivatives in M and x. So it doesn't look so easy to study mathematically and even more so to solve numerically. But it turns out that indeed it's possible to make a general theory of all those systems of equation. And this is a joint work with, as mentioned in the first slide, with Charles Bertucci and my old pal, colleague, friend, whatever, Jean-Michel Lasserie. Which maybe we were able to do maybe 20 years after we introduced the subject. So it took us I mean, we were pretty slow. It took us 20 years to learn how to check that those problems are in general well posed in a manner I would describe now. Next slide, please. Okay. So the first step, which makes some sense from, I don't want to emphasize the game theoretical aspects of what we are discussing, But typically, when you're dealing with game theory, you have to measure the decisions you make, and typically this is through like a valuation from a process valuation function. That's my little u. But more importantly, what you're really interested are very often the strategies. In control theory, it would be really like the optimal feedback if you're using dynamic programming, which is in some sense always a little more important, more important than the optimal cost, which of course makes sense and is useful, but clearly the real actions you have to take are more important to determine. So here, what this means is that we are going to go from the original equations, we are going to look at the derivative with respect to x. So the sensitivity with respect to the state variables. Okay, so it is now an unknown function taking values in RD, which is a gradient, although we completely forget it's a gradient, okay, which would be then an extension to situations where you are defining an equilibrium of strategy without any kind of value function really defined, which makes lots of sense in terms of game theory. Okay. So what you have here is now an equation which can be written. You still recognize the transport term. You recognize that's the A. I'm sorry. With the A dx u plus a c, this is really the differentiation of the decision block. Okay, so decision blocks was written as a nonlinear terms in the strategy, and now it becomes a nonlinear term in U, no more in dxu. And accordingly, the transport term can be written in that manner, okay? So you see that you have something which looks much more like the finite state equation I wrote a minute ago. I'm not describing anything about the noise. This will take a little bit of time. There is ignore the first remark in order to gain some time. I want to mention that we can allow for a full interaction. Full interaction means that not only the agents are being coupled through their situation, their states, and so on. So basically, you take your decisions taking into account the situations of all the other players. But you could have coupling in the strategies, which then mean that A, B, and C are dependent on something which is, I wrote gradient U, it's of cap U, it's gradient of small u. So this is really cap U, and it's the image measure of M by cap U. Okay, so that's how the interaction of strategy can be handled, and the mathematical results are going to be the same. Next slide, please. Okay, so you saw that this equation involves first-order derivatives, okay, possibly in infinite dimension, and that the first-order derivatives with respect to the measure involves other derivatives in x. Nevertheless, all those problems, all of them, assuming that the data are positive, and independently of the rather large generality of equations I just wrote down, they are all well posed. I'm sorry?
No, it's okay. It's
No,
okay.
it's okay. It's okay.
Okay, well-posed. Those are well-posed problems with, of course, an initial condition, which is supposed to be Lipschitz. So typically, we have lots of derivatives. And we are saying that there exists a unique solution up to a maximal time of existence, well posed in that sense, local in time, if you want. It's really a maximal solution, only by having things which are bounded in Lipschitz. Okay, so Lipschitz, what does it mean? Lipschitz means, of course, Lipschitz in X, that's in RD, and Lipschitz in M. And remember that M might be just arbitrary bounded measures. So typically, the only distance you can really use is the one Wasserstein, really the most control of its distance, right? So it's a W1 distance. So that's what it means. Lipschitz in X and M, that's Lipschitz in RD cross P1 or M1, which is a space of measures equipped with the Wasserstein, the one Wasserstein distance, which is nothing else than the W minus 1 norm, right? So it's that space, okay? But on the cone of non-negative measures. And although you have second order terms in the equation, we are saying only that the maximal the regularity one needs is only Lipschitz. So what does it mean? So it's not, even in finite dimension, it's not completely clear. Okay, so there are issues about whether one is working in the Hilbert space or in P1 because the notion of regularities are a little bit different. The fact that you could have interactions between the coupling between strategies is okay because this is image measures are Lipschitz operation in the correct distances. So I don't want to lose you with such details. So bottom line is that in general, we are going to have, and I'll be more precise in 2 minutes, that there is a Cauchy-Lipschitz-like theorem. Okay, so and the correct class of and the nice class of to make this problem well posed are paths which are continuous in time with values in space of continuous functions, so in Xm, and bounded in time with values with in the space of Lipschitz function. Couldn't it be continuous in time with values in Lipschitz? Because in some sense, that was Lipschitz would then mean C1, I mean, by out of continuity and stuff like that. So that's usually when you have Cauchy-Lipschitz theorem, you have things which are continuous with value in a certain space. Yes, continuous with value in a certain space and just bounded L infinity with values in a smaller space. Hence, the two spaces I mentioned some time ago. Next slide, please. Okay, so I already essentially mentioned everything which is there, namely that you have a maximum time of existence, which can be infinite, such that for all time before that possible blow-up time, you have a unique solution, which has the regularity I was mentioning, continuous in times in the series values in a space of continuous functions, etc. Is it really possible to go below Lipschitz? I don't believe it's possible in general, that you can do less than Lipschitz and to have a well-posed problem, but I don't have, I cannot really prove that this is optimal. I strongly believe it. There is no blow-up, and that's something we observed with Jean-Michel Lasry a long time ago, if some type of monotonicity assumptions are being made. So typically, if you think of Berger's equation, which is clearly an example of equation which fall into this huge collection of equations, namely du over dt plus u du over dx, you know that in general a singularity will appear, so there's going to be blow up unless the solution is monotone, okay? Increasing, non-decreasing. And so that's an if and only if for the Burger's equation, and you have here a similar structure, a little more complicated, but which that says that at least if you are monotone or close or something up to a change of variables, so well, whatever. If you are monotone, then you have no explosion. Okay. There is, of course, an important question, which is what happens after this blow-up time. Clearly, you can't expect to have uniqueness. You have a set of solutions, and we understand a little bit that indeed there are very interesting things happening beyond the first blow-up time, but it's difficult. I might come back a little later on. Such a uniqueness results and blow-up results, of course, indicate that, if you have a piece of a positive, if you have a smooth solution, it's automatically unique. It's automatically equal to that maximum solution. Okay, meaning of solution later on. I don't want to spend too much time on technicalities, but I'll explain very briefly what's going on. Next slide, please. Okay, so I'm checking on time. I will have to stop soon. Finite state space, is. You think that you have this nonlinear equation, and you look at a fixed point, and basically you see that in order to understand the distance between, very simple argument, the distance between two solutions, that's going to be okay if you know that at least one of them is Lipschitz, because there is a gradient u inside the equation. And on the other hand, you have a nonlinear estimate for the Lipschitz norm, which in general is not a linear estimate, so that's why you can't expect to have a global solution. Okay, so basically you want to use a second estimate to say that you can put everything in a ball of Lipschitz function. And once you're working in the ball of Lipschitz function, basically, thanks to the first estimates, you're in Cauchy-Lipschitz territory. Yeah? Hence, the fact that you're dealing with things which are bounded in the Lipschitz norm and which are continuous in time, in sup norm, in the space of continuous function. That's, in two lines, the idea of the proof. And in fact, there is an upside version of that involving than the other, but I don't want to end this on archive. Now, next slide, please. I'm going to conclude soon now. Yeah, a remark on Lipschitz. Let me pass this. Time is running. So just to mention that indeed you have one way to think about those things in general in an abstract manner. So next slide, please. Again, next slide. So in all cases, basically, you have a similar estimate that in a finite state space, and so you have to deal with which Lipschitz solution of the example equation I just mentioned. Noise involves some other equation. What does that mean? Solution of that equation? Because after Lipschitz, okay, derivative exists almost everywhere. Yes, but in finite dimension, not in infinite dimension. Here we have dmu. Okay, so what this means is that once you are looking at such a fixed point, you have to define Lipschitz solution of such linear equations. And what you're going to use are characteristics, or stochastic characteristics, to define solutions of linear equations. Okay, so typical characteristics, and I'm writing in stochastic ways because in general those are stochastic DEs, stochastic PDEs, and typically the estimates you need are going to be estimates on the Wasserstein distances on those objects. Okay, so that's a strategy of proof, and that's how you define Lipschitz solution, because that's not a lot of regularity to ask for equations that involves many derivatives. Okay, so I'm going to now conclude with the next slide to say that, as I mentioned already, singularities appear in finite time. Monotonicity condition yield global solution. And well, what we have are collections. I'm not going to show the last slide. What we understand are examples where we can have a collections of solutions, and also solutions make sense. So I've been involved, and we all know work which try to select the right solutions or weak solution, like entropy conditions, later on viscosity solutions. But here, I don't believe that makes sense. All those equilibria are of interest, and very often are of interest for applications. So we have examples that, and we have situations that we encountered numerically where we could see that in order to resolve past singularities, we have to make additional modeling assumptions. In other words, suppose that the population is in the situations where the two courses of actions are possible, and which one to choose. That's a typical singularity in optimal control. So in optimal control, the optimal decision criterion will tell you that, okay, at that point you may have two options, but nearby you only have one option, and that's it. That's how you're going to define in a consistent way your optimal controls. Here, that doesn't make sense, because there are lots and lots of players. So conditions saying, well, maybe we will all go to the left or all go to the right, assuming it's a left-right issue, and or we are going to toss a coin, and we are going to go left and right depending on the outcome of the coins and so on. But that's modeling. Okay, it's not something which is not given to you by just writing down the equations and the model. So I believe this is the right way to think about those things. But before we even try to make any kind of general theory, we need to accumulate more and more examples. Let me conclude with one word related to Enrique Zozo's lecture, because this topic has received a lot of attention. There are many applications. We even founded a startup company a long time ago, which has been sold after we reached 50 employees and so on. So there are real applications lurking behind everything I'm telling you. On the other hand, how are you going to compute anything there? So if you have independent noises, one can reduce all the action to a finite dimensional problem. Backward, forward set of PDEs, and computations are possible. In general, what about infinite dimensional computation? Okay, that's where two observations need to be made. One is that, and that's related to the curse of dimensionality that Enrique was mentioned, the famous expression coined by Richard Bellman. But in some sense, in many situations, although the problem may be I or infinite dimensional, the solution is not that complex if we are able to determine it. Okay, so in some sense, there are some kind of there is quite often a relatively smaller, I mean, a relatively, not a very high number of hidden variables, of course, you don't know them before you've solved the problem. Okay, how to detect them? Okay, so the first step is that indeed one can use neural nets, which are fantastic, and that's now by now very well understood from an harmonic analysis point of view, a fantastic approximation tool because you can generate everything you want with through neural nets. So you need lots of neurons, but not so many layers in order to do so. Okay. So I'm not talking about whatever that means, because this is not well-defined deep neural nets. I'm talking about things which are basically shallow neural nets. You may have 6 or 7 layers at most. And it turns out that we look at example coming from economics, and we were able to compute solutions of infinite-dimensional problems. Not only were we able to compute that, but this gave us the possibility of identifying some key variables. When you really investigate and you try through the layers, through the architecture, you try to find the so-called hidden variables. So we are finishing this on a very specific economical example, but I'm quite optimistic that the neural nets, what people call machine learning, or AI, to be more to speak in English, talk in English, can also be used not only to compute in high dimensions, to circumvent the lack of models and so on, but also to make the dimension reduction in modeling, okay, by identifying those hidden variables. The fact that many optimal decision problems are indeed not as high dimensional as they appear in terms of the solution was well summarized by a Nobel Prize in economics that a long time ago, specialists in game theory, a long time ago said that there are less strategies than there are players. Okay, and that's an interesting sentence, with which I will leave you, and thank you very, very much for the invitation and for your patience. Thank you, and a special thanks to Anna for helping me out.
Okay, thank you very much. Thank you very much for your talk. And we have maybe time for one question. Okay, let me ask one question. I think you have talked about it very briefly, but is it interesting to analyze the behavior of stationary solutions, and which is the interest? In
Yes.
the last slide, you have written that under some conditions, the existing time is infinity.
Okay. So thank you. So the indeed, the existence of steady-state solutions is a very natural issue, and makes certainly more sense when you have global solution than globally in time than in general. Also, one has to be a little bit careful in what one means with steady-state solutions. Because you have real steady-state solutions where you just say du over dt equals 0, and you keep the rest of the equations. But you also have, and that's very natural in terms of optimal control, where you say that first of all, you have to reverse time. So you have to argue backwards. So the initial condition becomes a final condition. That's in optimal control. That's natural. okay? Because that's the horizon of a problem is where basically you start the reverse time dynamic programming argument. Okay, so, and you let the horizon go to infinity. So that means that the interval in which you're solving the equation becomes infinite. But the du over dt doesn't necessarily cancel, because what you have is something where you don't have any initial conditions, and you may have a certain behavior as t goes to infinity. So that's a truly stationary problem, which is an infinite horizon problem, but there is still time dependence. So that's point number one. And among such solutions, you may have the ones that do not depend on time. So you see that this is a complicated story, and there are very interesting issues. But the first type of stationary problem I mentioned, which are infinite horizon problems, are very natural from an economical point of view, because quite often the horizon of the problem in economics doesn't make any sense. It's like a parameter that you don't know what it is. So this is there is a very important discussion to be made on such a generalized steady state problem, and this is really because the problem is infinite dimension. If it were finite dimensional, steady state is steady state. There is nothing to be said. But here, because of the transport part of the problem in a space of measure, you have to be a little bit careful about what one means by steady states, and both are extremely interesting. Many things to be studied there. Thank you, Enrique, for this very good question.
Thank you. Okay, thank you very much for your conference, and I'm going to stop here. And thank you to everybody.